Now springs oftentimes obey what we refer to as Hooke's law. And Hooke's law says that the force of a spring is equal to minus a constant of the spring, and that depends on how the spring is formed. Is it a coil spring? Is it a leaf spring? Is it strong? Is it weak? All of that comes into play. So that's just a constant of the spring times x, where x is the distance from some rest or equilibrium length of the spring. And to make our life simple, we're going to let x equal 0 at equilibrium, and we're just going to integrate from the equilibrium position. We can integrate from other positions, but it becomes a little bit uglier integral, a little bit more confusing. So we're just going to avoid that for now. We'll come back to it at a later time. So imagine, if you will, that you have a block attached to a wall by a spring, and the spring obeys Hooke's law. Now there are lots of springs that do not obey Hooke's law, but we're going to stick with nice easy ones. So that spring has a constant K. We'll make this equilibrium, so there's 0. And what's going to happen is we're going to pull the block to the right. Now some force is pulling the block to the right. I agree with that. But what's happening is we're only interested in the force of the spring and how much work it does. So I want to know how much work is done by the spring. So I'm going to call that W sub K for the spring, because the spring constant. It's going to be equal to the integral of F dot dx. We're just going to stick with one dimension for now. Just keep it simple for a little bit. And we're going to go from 0 to some other distant x, we'll just call that x for now, out to the right. In that scenario, I have the integral of minus kx dx. The force is to the right, the displacement's to the right, so those dot products go to 1. We integrate from 0 to x. The minus k comes out. I'm left with the integral of x dx from 0 to x. And the integral of x dx is x squared over 2. Evaluate from 0 to x. When I put in a 0, I get 0, so it's just going to be x squared over 2. So the work done is minus 1/2 k x squared. Now if instead you're going from 3 to 7 instead of 0 to 4, you're just going to have a different values, then you'll have to keep that in mind. If we went to the left, the displacement's to the left. The force of the spring now, because you're pushing against the spring, the force of the spring is to the right, so they're in the opposite direction. And so that's going to give you a negative work, but you get the same value, because when you put a negative x in here, it gets squared and it becomes positive. Okay, you'll notice the negative sign here, and that makes sense because as I pull it to the right, the spring is pushing back to the left, pulling back to the left actually. And that makes a lot of sense then, because you have force to the left, displacement to the right. There should be a negative sign. All right, so again, keep an eye out for signs for work. So a positive work indicates that work is done on the object, whereas negative work indicates work is done by the object. Just a couple of sign conventions to keep in mind. We'll work with them more as we run through problems. Okay, let's talk about kinetic energy. So kinetic energy, sometimes referred to as the energy of motion. It's only associated with moving objects. It might also be thought about as the work required to bring an object to rest. These are the things that we'll use to define kinetic energy. The equation for kinetic energy is 1/2 mv squared, 1/2 mass times velocity squared, or 1/2 mass times the dot product of velocity with itself. So once again, you're going to notice that there's no vector value here. Even if I use vector velocities to give me this value, I dot them with itself, and that's going to be a scalar quantity. So kinetic energy is a scalar quantity, and it must always be positive because you're squaring velocity, and the square of a number, whether it's positive or negative, is positive, and mass is always positive. So kinetic energy will always have a positive value. Take a look at units real quick. 1/2 has no units. Mass is in kilograms. Velocity is in meters per second. But then I square that, so I get kilograms meters squared per second squared, which is kilograms meters per second squared times meters. But that's a Newton times a meter, and that's a joule. So kinetic energy is the same units as work. So work and energy very much related. They are very much related to each other. So much so that we have this work and kinetic energy, the work energy theorem. We've defined work already this way. Okay, and you'll see I've used a U here instead of a W. That's the way the engineers will write it. So the work going from position 1 to position 2 is defined as the net force done dotted with dr. So this is net force, and that's very important. What we're looking at here is the work done by all of the forces acting on a system. All of the forces acting on a system. And that will equal then the change in kinetic energy. So 1/2 mv2, this is the speed squared. Notice I say speed because the vector quantity has been dotted with itself. I'm only looking at magnitudes. So this is the speed squared at position 2, and this is the speed squared at position 1. And so what I can do is I can take this term right here, bring it to the left-hand side of the equation, and the work energy theorem is right here. And it says that if I start with some initial kinetic energy, and I find the work done by all of the forces acting on an object, then I'll get the final kinetic energy of that object. So initial kinetic energy plus net work done equals final kinetic energy. So here's a little example. Let's give this a try. I have a graph here, force versus displacement. Right? Force is along this axis, displacement is along that axis. And I'm given that the mass of the object is equal to 6 kilograms. I'm told that the position, the initial position, which I've called S here, and that should be displacement. At this initial position, my velocity, so I'm going to call that velocity 1, that's equal to 4.5 meters per second. And I'm interested in the velocity at 8 meters, which is right here. Now keep in mind, what I'm going to do is use work and energy, so 1/2 mv squared, call that v1 squared, that's going to equal 1/2 6 kilograms times 4.5 meters per second, quantity squared. So that's going to equal 60.75 joules. Now what I'm interested in is the work done by the force. So that's the integral of f dot dx, because it's only in the x direction. And actually I've called it ds, so we'll use that same thing. But we need to recall then that an integral is the area underneath the curve. And so what I want to do is find the area underneath this curve. So I'll start off with this rectangle, and the base of that rectangle is 3 meters, and the height is 6 newtons. So the area of that rectangle is 6 newtons times 3 meters, which is 18 joules. So far I have 18 joules. And let's do this triangle. And the area of a triangle is 1/2 base, which is 1 meter, times height, which is 6 newtons. And so that's 3 joules. And I have another triangle over here. So the area of a triangle is 1/2 base. The base is 3 meters. And the height of the rectangle is -9 newtons. And so this does in fact have a negative area, and that's okay. So 27/2 is 13.5, so minus 13.5 joules. And we'll go to there. I have 1 meter times -9 newtons. That's -9 joules. And so I end up with a net work done, 21 joules, minus 22.5 joules. So the net work is negative, and that's okay. You can have negative work. So minus 1.5 joules. And so the final kinetic energy, 1/2 mv2 squared, equals 1/2 mv1 squared, but that's 60.75 joules, plus the work done, which is -1.5 joules. And so I get 59.25 joules. So that's the kinetic energy at position 8 here. Let's take it a very special case of the work and kinetic energy idea here. Let's assume I have a constant force. So F net is equal to a constant, but F is equal to ma. That's also going to be constant. And so what do I get? I get 1/2 m v1 squared plus the integral from r1 to r2 of ma dotted with dr equals 1/2 m v2 squared. But if I look just at the integral, ma is constant, so it comes out. So I have ma times the integral from r1 to r2 dr. But that's just ma dot with delta r. And furthermore, let's make this special case one-dimensional. And so in that scenario, the displacement, the acceleration are along the same dimension. Now one could be positive and one negative, but I'm going to end up with ma delta x. We'll just assume that it's along the x-axis since one-dimensional. And so what I end up with is 1/2 m v1 squared plus m a delta x equals 1/2 m v2 squared. You'll notice the mass is in each term, so it goes away. And then let's just multiply both sides of the equation by 2. And if I do that, I get v1 squared plus 2a delta x equals v2 squared. But you've seen this equation before. When you had a constant acceleration in one dimension, we wrote v squared equals v initial squared plus 2a delta x. Well, the initial velocity is v1, the final velocity is v2, so this really is the same equation. So you can see another way that we can gain this one-dimensional equation that we used way back in the first couple of weeks of this class. So it's really related very much to work and energy.